Okay, Stephen Farrington will present a machine intelligence for estimating soil water flux from soil moisture data.
Hi, I'm Stephen Farrington. I'm the owner and lead technologist at a small business called Transcend Engineering in Vermont. I just want to acknowledge my co-conspirators on this, Ty Foray, who's a professor of hydrology at University of Arizona. And by the way, Ty says, if I see you, to say hi. So hi for Ty. Dave Wessner, who's our computational hydrologist sitting over here. Kevin Powell, who's a machine learning data science guy and a software engineer, and Ben Levitt, who's a software engineer. And I left a name off because she left our company in January and I just wasn't thinking about her. But in phase one of this work, Andrea Elhaj. So Marena, I'd like to give you updated slides afterwards. Just quickly, this is a little bit of change of pace because we're a commercial for-profit entity, although after Ashish's presentation, I'm thinking of becoming a B Corp. We were doing an SBIR research project, and this is really geared toward commercial application of some practical soil moisture, soil flux stuff. So it's going to be a little bit different flavor, probably not as generalizable and academically rigorous, but anyway, this is the sort of belief statement that guides our company. We've been around since 2010. We work in these areas. We work with federal agencies. Like I said, we get SBIR grant funding. We get some BAA funding. We work with universities and public and private research institutes and industry. And our specialty is applying machine learning to things other than mouse clicks and social media posts, which, as people like Garrett and others in the audience who are doing this realize, is difficult when you get into the messy data of the physical world. So we set out to quantify soil water flux. Specifically, we focused on deep drainage below root zone and on root water uptake, two sort of unknown sync terms. Flux is obviously important. I'm talking to soil scientists, so I'm kind of targeted this at too low a level. But for the DOE's interest is because their biological environmental sciences group wants to better understand, coupled hydrologic and biogeochemical processes. And so quantifying flux is important to have that information. Our interest commercially is with water conservation, irrigation scheduling. We targeted almonds specifically because they use a lot of water. I read a statistic somewhere that said 3.5 gallons per almond. Now, a lot of that's recycled, and I don't think it actually takes, having been in the fields wading through the water, doesn't take 3.5 gallons to actually grow an almond, but they're just super conservative or liberal with how they use their water rights to make sure that they get their yield. It's also important, and if you think about obviously the amount of sort of latent heat of vaporization that goes along with any exchange of moisture between the atmosphere and the soil, very important in climate monitoring and modeling. There's regulatory applications, everything from landfill caps and covers to emerging recharge in California and things like that. Basically, if you look around at Campbell Scientific or Lycor or Meter Group or anybody else who specializes in equipment for measuring, soil water related things in the ground, you will find there are no like drop-in flux meters. That's because a lot of the techniques that have been published in the literature in the past and have been used are just not practical for commercial viability. I have to apologize. I'm going to go rapidly through these slides because I did not time myself before I submitted them. And when I went over it last night in a hotel room, I discovered it was like a 20-minute talk and I'm cutting things out as I go. So, basic problem is we got a mass balance. We got change in storage that we can monitor with volumetric water content measurements. But that doesn't tell the whole story because it can't tell you about through flux, right? Because water flow, there can be flow without a change in volumetric water content. And likewise, there can be, you can't really figure out what partition vertically things are going into, right? And then we have the two unknown, unobservable sinks for root uptake and deep drainage. And to understand all that from VWC, if you're going to do like a conventional inverse modeling approach, parameter estimation, whatever, you really got to know the soil water characteristics. And those are not easily obtainable in ex situ. They're never going to match what's in situ. So we got a problem. So we asked ourselves, can the hydraulic behavior of the soil be learned by watching long enough with great enough data density? Can it be learned by a machine learning algorithm? Such that information can be implicitly used in the solution for deep drainage. We kind of went for the holy grail first. We could have chewed off some easier steps along the way, but the commercial application was to figure out where the water's going, right? So Our hypothesis was that with sufficiently dense spatiotemporal data on volumetric water content over a long enough period of time, that a machine learning algorithm could learn what the soil's behavior is with regard to infiltration and drainage, and then from that could infer what these two sink terms are. Luckily, we had the ability to monitor in sort of extreme vertical resolution. This is work we did back in 2015, 2016 for Department of Energy, resulted in 2 patents. You can look them up, but we created a time domain reflectometry based continuous soil moisture profiling probe. It's not in commercial production right now because it's very expensive and it's very difficult to build the waveguide in a repeatable fashion that can be used. So if you have anybody you can hook me up with about that, let me know. Turns out we didn't end up needing that kind of data density. So machine learning can be very data hungry, especially something as complicated as phenomenology. You know, we're going to need time series. We're going to need to represent a lot of data vertically, right? And in time, we're going to need to have labeled fluxes, the ones we're trying to predict, and where are we going to get that data, right? Because there's not an instrument out there that measures that. I mean, there are a few sort of weighing lysimeter data sets and some heat pulse methods, but not in enough soils, not in enough scenarios of moisture dynamics and antecedent moisture condition to train a deep learning network. We're going to need to represent hundreds of different soils in their behavior, because you definitely want to sort of peg the parameter space and make your solution generalizable enough that it's got some utility. And we're going to have to pepper that with myriad wetting scenarios, including changes in intensity, duration, and antecedent moisture condition as a function of the history of that. So the question is, where do we get that data from? And so our approach, kind of the special sauce we've been doing on a number of projects for the last couple of years, is this sort of patent pending process of using process-based modeling to create a physics-informed machine learning framework. The left-hand third of this is basically the process-based modeling. In this instance, we used Hydrus as the sort of well-accepted and well-validated model of our Beto zone hydrodynamics. And we gathered realistic inputs from the irrigation recommendations of various like county extension services, UC Davis researchers, plus the actual practice we witnessed in the field. We have irrigation records from a number of almond farms we were on. And then we combine that with our understanding of the sensor technologies, because if we're going to build an ML that's going to take sensor input, that's not the theoretically perfect model data that comes out of the Hydrus model in terms of what the volumetric moisture content is at this point. The sensors introduce bias, they introduce uncertainty, they have drift, they have, each one has a different sort of spatial integration volume and a weighted averaging of the area of influence. So we characterize sensors off the shelf in the laboratory against laboratory standards. Chris Chambers will appreciate, we handled 1,4-dioxane water mixtures and some other techniques. And so then we create mathematical models of the sensor personality, and we use those models to adulterate the output of the Hydrus model to tell us what a sensor, you know, what's the range of values that a sensor would likely read in here. We do realizations of every sensor measurement over 15-minute or 1-hour time steps. And then, of course, with deep understanding of machine learning and the 1,000 ways you can overfit a data set without it showing up in your loss divergence, as Garrett will appreciate, we apply that knowledge as well with our sort of pathological data sets with proper loss functions that focus the attention on the decision-making process we're trying to support. Case in point, when we first did this in phase 1, we were getting astounding results. We still get astounding results, but in a more rational manner. But we realized that the long short-term memory network was just guessing that the flux was near zero every time, because only 4% of the cases were significantly greater than that. But those are the cases we're interested in. So all of our errors were at that end of the spectrum, and we're like, hey, we're nailing it 95% of the time. All right, so a lot of iteration there. There's iterative loops that aren't shown. I got to move along. This is just one example of a sort of a visualization. Dave is great at using the matplotlib stuff. Show what he's doing with his simulations. You see, we have variable root activity that varies by season, by maturity of the almond crop, by a number of other factors. We add random factors in. I already mentioned about sort of the irrigation schedules we use. We have sort of this Blatten hypercube sampling of the parameter space of these simulations. So we generate tens of thousands of these And they're each like 50 days long. And then we can choose slices of time, independent slices of time in those as training examples and test and validation examples for the long short-term memory. These are the different off-the-shelf sensors we have characterized so far. We're working on Sensoterra, but we're way behind on that because it took us forever to get the LoRa working. And I wish I knew about Patrick's expertise before then, because we could have asked him how to help us there. Anyway, these are the depths they measure at. And we're working to add more sensors, like scan array arrangement with maybe the TDR315 or whatever was previously used, the Hydroprobe, Hydrosent. I don't know Stephen's naming convention. Anyway, this is the just a sort of a pictorial representation of our cloud-based simulation framework. Bottom line is here, we can generate sort of stochastic variation in the inputs and then run tens of thousands of simulations in a day with elastic computing in AWS. And I really want to emphasize this because this data set, our ability to generate these massive training data sets based on, well-accepted process-based physical models, I think is an asset for answering all sorts of questions about soil moisture and soil moisture dynamics with machine learning. And I want you to be aware of that. So I actually didn't include a slide on the machine learning model, but it's like a 5-layer deep multi long short-term memory recurring network. And that architecture was arrived at through a lot of trial and error as to what was sufficient and necessary. You don't want to overbuild these things because then it becomes an ill-conditioned problem with too many internal parameters. And then we do Bayesian hyperparameter optimization. We do various methods for validation, leaving out reserved data sets. This is one example of one of the probes. This is a particularly good one because EnviroScan, we declared the deep drainage horizon at 120 centimeters for almond root zone, and EnviroScan gives us a couple of measurements below that, which really helps with our prediction. If we were to put the SoilView 10 in this crop, doesn't do as well, but it does great in citrus where it's at 65 centimeters. So you can see the R squareds we're getting fundamentally the heart of our loss function is root mean error, but weighted across the distribution. And so there's also another clever visualization by Dave where he's got the density of points that are in these clouds so that you can tell what's there represented in color. So that's a mislabeled axis here. That's actually deep drainage, not root water uptake. This is with an array of Teros 12 sensors every 4 centimeters every 4 inches from 4 inches deep to 36 inches deep. That's one of our ML endpoints as a configuration. And I've got the similar results, but didn't want to include too many slides because of the time limit for the other probes. These probes listed over here are the ones we're initially supporting. Because this is a commercialization effort with SBIR grant, we have, our product is an API as a service. It's going to be released in AWS Marketplace. The minimum viable product is going to start with almonds, then we're going to move on to coastal lemons and navel oranges, simply because that's a market decision based on the advice of our commercialization partner, Landscan in California. Significant results of this. So we created and applied a framework for physics-informed machine learning. The ML models we developed using it appear to be understanding soil hydraulic behavior well enough to do very accurate prediction of critical fluxes. Turns out we don't need the data density in vertical profile that our PRISMS technology provides. We can do it with off-the-shelf multi-level sensors and with discrete sensor arrays. But we do account for their personalities, which we rigorously quantify and express mathematically so that we can introduce the noisiness of inputs to the machine learning model during training that it needs in order to be robust and generalizable. I can't emphasize this next point enough, and that is that this really was a multidisciplinary effort, and it required all the disciplines interacting all the time and doing rapid iteration and updating results and figuring out, like redoing the simulations. Like we didn't have enough variability in root water uptake, and that was short circuiting the solution. And we didn't have enough range of overwatering to accurately represent what was going on in the almond crops. So we expanded that, and then we just kept adding variability and random stochastic influence in the data sets to the end. Now we have tens of thousands of these simulation scenarios over, nearly 2 months each. Very rich data set. And this, the scope of this and our focus was driven by our desire to, reach rapid commercial maturation. And the main point I want to share with you is we have this infrastructure, we have this understanding of soil physics, of sensor physics, of machine learning, and we would love to work with anybody to pursue trying to solve more research questions about how we can apply this sort of physics constrained framework to trying to reveal hidden variables that are very difficult to measure by inferring them with machine learning. So with that, we have time for questions.
Thanks, Evan. Yeah, we do have time for some quick questions.
Oh, I better get my funding acknowledgement up here too.
Mike's gonna get some exercise run back.
That was really awesome. Thanks for going so in depth with all of that. Synthesizing data is something I've never delved into, but I've been really interested in. So that seems really impressive, like the amount of synthesis that you all worked on. One thing I was wondering about based off of the conversation that we had yesterday was, now that you have a working model to synthesize training data, I'm understanding that correctly, right?
I'm sorry, I didn't quite get a working model.
That synthesizes training data for your ML model.
Yes.
So now that you all have that, I was thinking about generative adversarial networks for, their sort of state of the art for synthesizing, we see them for synthesizing images or other things like that. But I never thought about them in context of synthesizing data for training another ML model. And I was wondering if you all had considered that, and if so, kind of what your thoughts are on it.
Yeah, sure. So GANs are great for imagery when the goal is to make it appear in a manner that could fool a human or could fool the adversarial network that you're up against, right? I'm not familiar with the literature on sort of time series data and GANs for recurrent network type problems. But I will say this, I have a visceral sort of anti-GAN reaction, because the thing about machine learning models is they key on features that humans aren't necessarily good at keying on. And there may be features that are not actually relevant to the problem, that when you are using one trained network as the standard to generate data using a GAN, you're not certain you're capturing all the relevant physics, because you're just capturing enough to make the benchmark or the reference model believe that you're generating realistic data, right? Case in point, I have colleagues at a company that does work for the US Navy, and they didn't have enough voice data to train their voice recognition language processing stuff to interpret commands over the intercom. So they were synthesizing them using a GAN, and they're doing sentiment analysis stuff and things like that. And I'm like, you're only capturing sort of the spectral features that are important enough to this one neural network. You're not necessarily going to be able to generalize to what's happening in the real world, right? So anyway, that's my long answer about using GANs for this type of problem. I don't see enough evidence that they're ready for this. I think we're going to find a lot of GAN work is going to have holes in it going forward. And I don't want to do that in like sort of safety or ecologically critical applications.
All right.